Good afternoon, good afternoon, dear colleagues. My name is Aytakin Aghayeva. I am from Azerbaijan State Oil and Industry University, French-Azerbaijani University, Baku, Azerbaijan. Today, I would like to present my research work entitled Low Temperature Thermodynamic Study of Cadmium Antimonide, investigated by means of electromotive force measurement method. And this study, I focused on cadmium antimonide, which is intermetallic semiconductor material. The main purpose of this work was to determine reliable thermodynamic functions of cadmium stibum using the low temperature EMF method. And the research motivation of this research is connected with sustainable energy materials. Today, one of the important problems is the effective use of waste heat. A large amount of heat is lost in industry, electronics, and energy systems. Thermoelectric materials are very interesting because they can convert heat directly into electricity. Also, thermoelectric materials can be used for solid-state cooling. This means cooling without moving parts and without traditional refrigerants. So such materials are important for compact, environmentally friendly and energy-saving devices. Cadmium stibum is considered as one of the promising intermetallic semiconductor materials for thermoelectric applications. So therefore, it is important to understand not only its physical properties, but also its thermodynamic stability. The efficiency of thermoelectric materials depends on several connected parameters. The first important parameter is electrical conductivity. A good thermoelectric material should conduct electrical current well. The second parameter is the Seebeck coefficient. This coefficient shows how much voltage is generated when there is a temperature differences. The third parameter is thermal conductivity. For thermoelectric applications, low thermal conductivity is usually favorable because it helps to keep the temperature gradient. Another important parameter is Hall mobility, which gives information about charge carrier transport. So the best thermoelectric candidates should have good electrical transport and low thermal conductivity. Cadmium stibum is interesting because it has semiconductor behavior and relatively favorable transport properties. Cadmium antimonide, cadmium stibum, belongs to the cadmium stibum binary system. It is an intermetallic semiconductor. This means that it has both metallic and semiconductor features, which can be useful for functional materials. Cadmium stibum is also interesting because it has low lattice thermal conductivity. This property is important for thermoelectric materials. However, to evaluate cadmium stibum correctly, we need reliable thermodynamic data. Thermodynamic functions are necessary for understanding phase stability, phase equilibrium, and for creating or improving thermodynamic database. That's why cadmium stibum was selected as the object of this study. Also, cadmium stibum is a promising material. Its thermodynamic properties are not fully clarified. In the literature, some thermodynamic information is available, but most previous data were obtained mainly from high temperature EMF measurements or vapor pressure methods. In some cases, these methods gave different results. This means that the available thermodynamic data are limited and partly inconsistent. Therefore, reliable low-temperature thermodynamic data are needed. In this work, I study cadmium stibum by EMF method in the temperature range from 300 to 450 Kelvin. This low temperature interval allows us to obtain more reliable standard thermodynamic functions close to room temperature. The main aim of this work was to determine reliable thermodynamic properties of cadmium stibum using the low temperature electromotive force method. In this research, two groups of thermodynamic functions were determined. First, the partial molar thermodynamic functions of cadmium in cadmium stibum alloys were calculated. Second, the standard thermodynamic functions of formation of cadmium stibum were obtained. These include the standard Gibbs free energy of formation, the standard enthalpy of formation, and the standard entropy of formation. These values are important because they show the thermodynamic stability of cadmium stibum under standard conditions. For EMF measurement, it is very important to choose the correct two-phase region. In this work, alloys were selected from the cadmium stibum plus stibum two-phase region of the cadmium stibum binary system. Two compositions were prepared. The first alloys contained 70 atomic percent antimony and 30 atomic percent cadmium. The second alloys contained 54 atomic percent antimony and 46 atomic percent cadmium. According to the cadmium stibum phase diagram, these compositions are located in the cadmium stibum plus stibum two-phase field. This is important because equilibrium two-phase alloys provide stable electrode behavior during EMF measurements. The alloys were prepared by the co-melting method. First, high purity cadmium and antimony were taken in the required atomic ratios. Then the elements were placed into quartz ampoules. The ampoules were evacuated to remove air and oxygen. After that, the samples were melted together. These steps allowed cadmium and antimony to react and form the required alloy. Then the samples were annealed below the solidus temperature from about 100 hours. Annealing is necessary because it helps the samples reach equilibrium. As a result, equilibrium two-phase alloys from the cadmium stibum plus stibum region were obtained. After synthesis, this phase composition of the alloys was checked by powder X-ray diffraction. XRD analysis is very important because it confirms whether the required phase are present in the sample. In this slide, the XRD pattern of the synthesis cadmium stibum alloys is shown. The alloys with 54 atomic percent antimony and 46 atomic percent cadmium showed reflection belonging to cadmium stibum and stibum. This result confirms that the samples is located in the cadmium stibum plus stibum phase region. This confirmation is necessary because only a correctly prepared two-phase electrode can give reliable EMF values. For EMF measurements, a concentration cell was assembled. The electrochemical cell can be written as cadmium solid electrode, then glycerol plus kalium chlor plus cadmium chlor electrolyte, and then cadmium stibum alloy electrode. In this cell, pure cadmium was used as the reference electrode. The cadmium stibum alloy from the cadmium stibum plus stibum two-phase region was used as a working electrode. The electrolyte was based on glycerol Kalium chloride and small amount cadmium chloride provides cadmium ions in electrolyte. The electrolyte was prepared under vacuum, remove moisture and oxygen because these impurities can affect MAF values. MAF values were recorded only after long stabilization when the system reached equilibrium. The EMF measurements were carried out in the low temperature range from 300 to 450 Kelvin. This temperature interval is important because it is close to standard conditions and helps to reduce uncertainties connected with high temperature measurement. A high precious multimeter was used to measure the EMF values. Before recording each value, the system was allowed to stabilize for a long time. This was done to make sure that the measured EMF values were equilibrium values. Stable EMF values are necessary for accurate thermodynamic calculations. The experimental EMF values were proceed using the least squares method. The temperature dependence of EMF was described by a linear equation. E equals a plus BT. Here E is an electromotive force, T is temperature, and B are constant. For each alloys, the coefficient and B were calculated from experimental data. A linear dependence of E and temperature is important reliability indicator. It shows that the electrochemical cells work stable and reversible in the selected temperature range. After obtaining the EMF equations, they were used to calculate thermodynamic functions. The thermodynamic calculations were carried out in several steps. First, the partial molar thermodynamic functions of cadmium stibum alloys were calculated at 298 Kelvin. Then the potential forming reaction method was used for cadmium stibum. Finally, the standard integral thermodynamic functions of cadmium stibum were determined. The calculation functions include standard Gibbs free energy of formation, standard enthalpy of formation, and standard entropy of formation. These functions are important because they characterize the stability of cadmium stibum can be used for comparison with literature data. The main result of this study that refined low temperature thermodynamic data for cadmium stibum were obtained. The partial molar function of cadmium stibum alloys were determined. Also, standard thermodynamic formation function of cadmium stibum were calculated under standard condition. These results help to refine the exciting thermodynamic data of cadmium stibum. They also complement earlier high temperature studies. The obtained data are useful for phase equilibrium analysis and for electronic thermodynamic database. For the functional point of view, this information supports the evaluation of cadmium stibum as a thermoelectric material. To conclude, low temperature EMF measurement were successfully applied to the cadmium stibum compound. The cadmium stibum plus stibum two-phase region was selected for investigation. The synthesized alloys were confirmed by XRD analysis. The EMF values showed a linear temperature dependence in the range from 300 to 450 Kelvin. Using these EMF data, the standard thermodynamic functions of cadmium stibum were determined. The obtained results are important for understanding the thermodynamic stability of cadmium stibum and its potential as a functional thermoelectric material. The key message of this work is that Low temperature EMF measurement provide reliable thermodynamic information of cadmium antimonide. Thank you very much for your attention.